All right, thanks everybody for joining online as well as here in person. I'm really delighted to introduce Vijaya as our next speaker. Dr. Kolachalama is a member of the Center for Brain Recovery, but he's also a faculty member in many departments and units in the university, including his primary appointment, which is in the Department of Medicine and Computer Science at Boston University. He is a founding member for the Faculty of Computing and Sciences at BU. He's the Whitaker Cardiovascular Institute at BU, the Evans Center for Interdisciplinary Biomedical Research, among other things. And his areas of interest, as you will see today, are computational biomedicine, neurodegeneration, pathology, and computational learning, which is what he's going to talk about today as well. He's been funded by American Heart Association, NIA, and HLBI, National Cancer Institute, the Artificial Intelligence and Technology Collaboratories with the Aging Research Program, and a few foundations as well. So, wow, busy man, but thank you for taking the time and coming today. This is an excellent opportunity for us because we just finished reading a paper on dementia in our lab meeting just now. So this is awesome. And then what we'll do is we'll take questions at the end through the audience and with them. Thanks.
Thank
Welcome.
you. Thank you so much for giving me the opportunity to talk today. Hopefully people online can hear me. If not, just maybe raise your hand. Hopefully people here can hear me. Okay, thank you. So I'm going to look at you because I'm also going to look at the screen and maybe look at people who are actually here to sort of interact. So as I kind of started to think about what kind of a talk I should give at Center for Brain Recovery, and as I've been kind of working very closely with Dr. Kiran, I've realized that there are so many things that I think are related to brain recovery, so many technologies that are coming up. And I was actually struggling to what to present here because we work on a few things. And at that same time, I realized that ultimately, at the end of the day, if you want to think about brain recovery, we also want to think about what kind of technologies we want to sort of use or think about, and also the data that we want to collect. So as the trend in terms of collecting more and more data is evolving, because I think people are now collecting more varieties of data, multimodal, if you will. Digital data is something that I think is coming up. So I thought maybe I'll focus my talk today to really explain about how potentially we can think about methods that can allow us to process all this kinds of data that is being collected, both within a clinical setting, as well as in hopefully a more naturalistic setting, with the idea that we can use modern machine learning approaches to process all this data and see if we can come up with something meaningful that can help us to assess, let's say in the case of this here as a case study, dementia, right? But of course, brain health is much more broader, but at least here I want to focus on dementia. If I can go to the next slide. Yes. So my agenda is, again, I want to give a very brief overview of machine learning, but then I also want to touch about two different topics. One is about collecting clinical data. So I think it's important to keep in mind, right? So digital data is still new. So it's not done in the clinical setting. So there is a lot of data that currently people already collect within a clinical setting. So that's one of my first things that we work on, which is how do you sort of process all this routinely collected clinical data to hopefully build methods that can allow us to assess dementia. And the second is to think about this future, hopefully, one day when we start collecting about all this digital data, how can we use that information to see if we can assess dementia, right? So those are the two topics. So, and first, before that, I want to talk about, or at least give an overview on machine learning. So I kind of want to start off by this generic concept in kind of modeling a task, right? So let's say we consider the problem of deciding, whether a patient has Alzheimer's disease, or, when given a large number of numeric input variables. And these input variables basically represent the characteristics of that patient, right? So one standard approach, which I think you may all know, which is to simply use this logistic regression, which you're seeing on the left side, that kind of simply estimates how to weight each of those input variables so that their weighted sum is basically a good indicator of somebody having Alzheimer's or dementia, right? So it's a simple thing, which I think probably most people are familiar with. You basically take all those input variables, you figure out the weights, and then you sort of learn from those weights and figure out what those weights are to see if the overall estimate based on those weights and those input variables can allow us to assess somebody who has dementia or not, right? But as you all know more than I do, Alzheimer's disease or dementia broadly is very complex. It often involves complex interactions. So if you really want to model this correctly, then we need to add extra inputs, or we can add extra inputs. And I'm going to use a term called interaction terms, which means basically talks about adding those extra inputs. And each of those interaction terms, they represent this product of two or more different input variables, right? So if this multi-way interactions have to be modeled, this is important because if you really want to model these things correctly, the number of interaction terms, they kind of increase exponentially, could go really high and high. So the neural network alternative is to add this, what we call as this hidden layer that you're seeing there, the orange layer, or hidden layers, is to sort of really think about add this layer to sort of model that interaction terms, right? So, and each of these interaction terms, basically they represent, the product of two or more different input variables, essentially. So, but if this whole thing is to really think about how to understand these hidden layers, how to sort of model these interactions. And the first step to determine that kind of which hidden factors are active, because not every hidden factor is active. Some of them are active, some of them may not be active. Some of the interactions have to be modeled, some of the interactions do not have to be modeled. So this is where I think where the neural networks come to play. And I think there is a value in terms of thinking about these modern machine learning architectures to allow us to sort of understand these interaction terms, right? So that's kind of really the basic idea of thinking about logistic regression versus neural networks. You could think of this second thing that you're seeing on the screen as a bunch of different logistic regressions, essentially, right? So that's kind of really the concept. But when it comes to more complex data, or let's say imaging data, for instance, right? So imaging is a very interesting data modality because it's somewhat structured, but also a lot of people call it unstructured. So in my opinion, I think it's a beautiful data representation because it can talk a lot of things in terms of the visuals. Like for instance, as you are seeing here is just a person's image or the selfie of the person. But if you really want to identify the identity of that person, what you're looking at here is these pixels, essentially, that are aggregated together to form a structure, which essentially represents the face of the person. So now if you want to really think about how to do this face identification task, or if you want to think about how to essentially learn a good set of those hidden factors that I just talked about before, is to basically repeat that kind of these hidden layers by modifying the weights on these connections from the input variables to the hidden factors, and the weights on those connections from the hidden factors to the output variable. So I know I'm talking a lot of these things, but essentially what I'm trying to say here is that if we are trying to understand those relationships between those different pixels, because if you have to identify the face identity of the person, we have to understand how those pixels are interacting with each other, right? So this technique that we use in neural networks to model these hidden layers is driven by something called as back propagation, which essentially became a very big breakthrough in neural networks. Because if you're thinking about multi-level interactions, multiple different variables involved, many hidden layers, we're talking about millions of parameters. So if you have to model these millions of parameters in a computationally reasonable way, it's not that feasible. So I think about 2 decades or 3 decades ago, a person called Jeff Hinton introduced this idea of back propagation, which allowed us to sort of really think about how to use neural networks to process all these different things and sort of understand these different hidden layers as well, right? So this back propagation technique brought almost like 1,000-fold efficiency in terms of understanding the parameters or estimating those parameters, right? And I want to talk a little bit more about imaging because I think this is an important data set. So here, what you're seeing here is in the context of, again, images, there are certain deep learning approaches. I think the term deep learning is used essentially to, what you saw on the slide before, are these multiple different hidden layers. So essentially the neural network became deep or long, pretty long, right? So that's why the term deep learning came to play. And one of the, at least in the context of images, there are certain deep learning approaches called as convolutional neural networks, that kind of essentially exploit the structure of the image itself, right? So in this case, what you're seeing is this is just a natural image of a bird, right? So if you're seeing the bird and I want to understand whether it's actually, whether that image represents something like a bird or a cat or something. And the way we want to do is we want to zoom in. And if you zoom in, you see these different, can I use my mouse here? I don't know where, this is the mouse, right? Should work. Okay. Oh yeah, so hopefully people on Zoom can see my mouse here, right? So I'm simply think about, I'm zooming this area here. And if I zoom in this area, what I'm looking at is a bunch of different values, which are essentially the intensity values or pixels, intensity values of those pixels in that specific region. So, and these are all different numbers, and together, all these different pixels represent that bird. But obviously, I want to understand. I want to teach the computer that this image represents the bird, which means I have to go zoom in and see what those pixels are or those pixel values are, right? So here I'm simply doing a very simple operation called as convolution. So, and this operation is very simple. If you look at it on the top, the 3x3 row here has values as 301, 262, 241. That's essentially the original signal intensity on that image. And what I'm doing is I'm taking this another 3x3 matrix, which is -1, 0, 1, -2, 0, 2, -1, 0, 1. I'm multiplying this 3x3 matrix with this 3x3 matrix in this fashion here. Simply, which means the -1 on the top left gets multiplied with 3, and then the 0 gets multiplied with 0, and so on. And then essentially I got a -3 value. And the -3 value is what I'm putting it as a representation of this 3x3 matrix getting convoluted to get a simple value of -3. I'll explain what that means in a second. So what I'm trying to do simply here is I'm taking that image, which basically zooming in, taking the values exactly of the intensity, and then multiplying with what I call as a filter, or let's say the weight, and then trying to represent that 3x3 pixelated information in a single value, which is -3. If I keep doing this multiple times, what will happen? The whole huge matrix of pixel image essentially becomes a very small vector of values. So as I keep doing it, I have a deep neural network, layer by layer, forms a operation, and essentially gives me a simulation of that, which I have learned by doing this process of convolutions. Essentially, what I'm now doing is I'm taking this huge matrix of data, which is this 2x2 image, into a simple vector of values, which essentially become then my signature that image represents that bird. So here, the learning part is essentially how do I figure out what is the best filter to learn so that I can best represent that image that as I sort of process all these different images, right? So that's the whole idea of a neural network. Essentially, what I'm trying to say here is that this neural network that I want to train on these bunch of images is simply trying to learn this filter. If I learn that filter very well, I can represent that specific image in the perfect way possible and create a signature coming from that image, right? So that's the whole idea of these neural network, right? So, and the other part, which I think I also want to spend a little bit of time is, when we talk about these deep neural networks, everybody say, what, it's just too complicated, too many millions of parameters and everything. Essentially, this looks like a black box. But essentially, what we are trying to do is we're trying to somehow want to come up with ways to go back into those neural networks and see exactly how we can understand how these neural networks are learning a specific signature in the data, which means we are trying to somehow figure out ways to interpret how these neural networks are making those decisions so that we are trying to open up that black box. So that's the background I want to give on machine learning, but I'm happy to take any questions here. But if not, I can move forward. Okay. So currently what we are doing is we're building those approaches, like I said, talked about neural networks, convolution neural networks, or other deep learning approaches to ask some simple questions, which is how can we basically take routinely collected clinical data and then see if we can process all this multimodal data to assess if somebody has, let's say, dementia, and if so, what kind of dementia they may have, and what are the underlying causes of those dementia, right? I think this has hopefully a lot of implications because these days, we have a pretty huge shortage of neurologists. So hopefully what we are trying to do is trying to build these tools that can hopefully be assistive in a clinical setting. And before we start building these methods, one of the first thing we do is we collect a ton of data. Not just data from one single place, but data coming from multiple different centers around the world with many, many, many collaborators around the world who have been very generous in terms of sharing their data with us. And as you can see on the screen, there are data sets coming from Australia, there are data sets coming from obviously the US, and also in the center that you can see here is this BU owned data, which is called as the Framingham Heart Study, where BU is the headquarters of this this cohort, which is based in Framingham. They've been collecting data over decades now. And although the name says Framingham Heart Study, they have been focused on the brain aspect since 99, I think. So they have a lot been collecting on the participants. Basically, these are the people many decades, and their kids and their grandkids are all part of the study. And they have generously provided their time to be part of the study. They come to the site, they do all the assessments, and they also allow us to get their scans. So we've been collecting all this data and their health records and etc. So that's a precious data set that we have access to. And it's important because Framingham Heart Study is not a clinical data set. It's if you go to, let's say, Boston Medical Center or MGH, those are patients data sets, right? So that's more clinical data set. But here, this is what we call as a community cohort, which I think is important because if you want to somehow do research and if you want to translate that research into a world which is outside the clinic, we want to think about how these models that we build can be translated to these kinds of settings. And that is why the Framingham Heart Study dataset has been extremely useful for us in terms of evaluating our models beyond the clinical setting. And the other thing that we also do is we collect data from Boston Medical Center. I'm not sure how many people know here. Boston Medical Center is one of the largest safety net hospitals in the nation. And the diversity of the data set that we collected BMC is much more than many other clinical centers. And that also brings us a purpose of why we are doing these, because again, if you're trying to build models, we want to make sure the models work on as many different data sets, different diversities, etc. Very generous again for us to give access to this data set, of course, with all the approvals and final set from BMC. And the reason I'm mentioning about all these data sets is because it is important to realize that if we start thinking about machine learning or data science broadly, at least in the context of healthcare, I think as of today, at least you can say that there are so many tools that are out there that you can potentially apply as you start thinking about a specific clinical question. But I think the challenge is to sort of think about building these tools that can hopefully work across different populations, right? So it's important to think about collecting data from multiple different places to make sure your models that you're building have some generalizability across just one data set. So that's why we spend a significant amount of time to collect this data. And after collecting data, we spend a significant time to actually process the data. Because as you can see here, the amount of time we actually spend on deep learning is about just 25%. A lot more time we spend is on taking that data, collecting all this from all these different codes, processing all of it, harmonizing it, normalizing it. And especially in the context of imaging, we go through a completely very long and boring procedure of processing all these images to make sure they are fit or amenable for machine learning, because we need to make sure the data is actually amenable for machine learning. So that's where we spend a significant amount of our time. And I want to give you some examples, right? So here, as you can see, is one process called as registration. And I'm sure people here are familiar with neuroimaging, but in the context here, what we do is we have built automated pipelines where you take these 3D volumetric data sets, and this one on the left side here, you're seeing a source image, and B here, you're seeing a target image. And what we do is we apply these triplanar registration process across every slice by slice in all the three planes to make sure that the source image is aligned with the target image. So that's one of the important things we do, because we want to make sure all these images are registered to a certain template, standard templates, before we start running our models on them. And then what we also do is we remove things that are hopefully not necessarily needed in the context of processing this data. So this is a very tedious process. Although I would say 90% of it is automated, we still have to do some manual work to remove the bright spot around the brain, the skull, to see it's not basically influencing the neural network training, because we feel like there is a high contrast on those regions, and we don't think it's necessarily needed for us to process what's actually inside the skull. So we do the skull strip process. This is also volumetric. There are some automated frameworks that are out there, but we still have to spend a lot of time to go back and do some QC on them. So these are all the different steps we do in terms of data processing, image processing, normalization. And after that, we are ready to sort of build these frameworks. Right here, I'm giving an example, which is a work that was published recently in Brain, where one of my PhD student, Shangran, who just graduated and he's now at Microsoft, he built this framework where he took these volumetric scans. And then rather than thinking about the entire scan as a whole, he created this what he called as a patch-based framework, which means he randomly tried to select, though you see those tiny cubes, the yellow cubes. So what he did was, instead of processing the whole brain, he took those tiny cubes and then ran through this convolution neural network that I talked to you earlier. And then he collected all the information that came from those tiny patches, and then collectively came up with a signature, which created this interpretable representation of the regions that turned out to be highly associated with the output of interest. In this context, it was whether the person has, let's say, signs of atrophy, which points to Alzheimer's or not. So in this way, he basically leveraged a 3D volumetric data set. He also leveraged this machine learning architecture called convolutional neural networks. And at the same time, he was able to come up with interpretable three-dimensional heat maps that not only allowed him to classify which person has that indication of Alzheimer's, but at the same time also allowed him to create those heat maps that sort of pointed to regions that turned out to be important in terms of making that classification. So he was trying to achieve all those goals simultaneously, which made it sort of an innovative approach to think about how we can not only accurate frameworks, but also that also allow us to explain what's going on. And then he did a few more things, which was like combine the imaging information with other data sets. Like, for example, in this context, he combined imaging data with some demographic data like age, gender, etc., to see how those classifiers can sort of do better in terms of understanding who has Alzheimer's and who does not. Right. So, and in addition to building, the first thing we did was we wanted to make sure the models that are trained on one cohort also work reasonably well on the other cohort. So these data that you're seeing here, or the results, sorry, that you're seeing here, are coming from these other cohorts that we collected. And then the model that was trained on one seemed to reasonably predict on the other data sets as well.
What is MRI and IN?
So MRI here, it's a good question. Sorry, I should have explained that. So MRI here stands for that model, which was just based on imaging alone. And NI is basically data which is non-imaging, which is all the demographics. And then obviously fusion is something where it combines all that information. And interestingly enough, I'm going to show you stuff on the next slides, is that in the context of understanding if somebody has dementia, we've learned from the neurologists, and we also saw that from our results, is that imaging alone does not play a major role. Whereas the symptoms and the other cognitive assessments done in the clinic turn out to be more important in terms of assessing if the person has, let's say, healthy cognition or mild cognitive impairment or dementia. And in one of the slides, I'm going to also, so that was one of the work where we just, like I said, came up, Shangran, my student, came up with an interpretable approach to process all those MRIs. But then we realized that there is a lot more data that you normally collect in a setting. As you can see here, on the bottom left, you have all these demographics that you would collect, as some neuropsych tests that people do, some functional assessment, obviously medical history, family history, all those is also available, which essentially is non-imaging data. Was we sort of expanded our mission to not just think about whether the person has, let's say, Alzheimer's or normal cognition. Here, we asked a much harder question, which was, okay, in this data set, which is multimodal, which is demographic, patient history, family history, medications, neuropsych testing, functional assessments, neuroimaging, can you process all this data, or can we come up with a framework that can automatically process all this data and then tell if the person has healthy cognition, mild cognitive impairment, or dementia? And if the person has dementia, can we identify if that dementia is Alzheimer's disease or due to some other etiologies? So we went for the one step further about what kind of questions, in fact, a clinician would ask if they see all this data. And in addition to creating that framework, we also validated systematic way, which means, we clinicians who were asked the same question. We also brought some, when I say clinicians, I'm talking about neurologists who were asked the same question, and similarly neuroradiologists who also look at these imaging data. And finally, also, we had some postmortem evidence on some of those cases to see whatever those interpretations that the model was trying to give were actually in those same regions where we observed some neuropathology, right? So we did all those things here, and this was work published a couple of years ago. And again, this is basically a list of all the things we've collected. And I say multimodal, I mean it, because it's really coming from different modalities, including imaging. Obviously, psych assessment, there is a very long battery of assessments they do, and of course, patient level history and demographics as well. And the framework that we draws from the slides that I talked to you before, which is taking those data, convolutional neural networks, but at the same time, once these neural networks process those 3D, we combine that with other, and then combine those two frameworks, because those logistic regression frameworks, but the convolutional networks work well with imaging data to sort of ask that same question. As healthy cognition, MCI, mild cognitive impairment, or dementia. And if the model tries to predict with high probability that the person has dementia due to Alzheimer's or due to other etiologies. And because of the fact that we were able to understand which factors can contribute to that prediction, what you're seeing on the left side is this SHAP analysis. I think we were just recently discussing with Dr. Kiran about how we can propose these things in some of the work that we could do in the future. Is these models allow us to go back and then see which of those factors actually are contributing to the output of interest. And because we asked two different questions, right? So one is about NC, MCI, and dementia. On the left side, you're seeing is a list of all those features coming from the multimodal data that turned out to be contributing more importantly to the output label of interest. And first one is MMSE. I don't know if you heard about it. It's a mini mental state exam, which is a very commonly done exam in a clinical setting that turned out to be the most important feature to make that first prediction. But on the other hand, to differentiate between people who have dementia due to Alzheimer's and other etiologies, MRI turned out to be an interesting or important feature, right? So it's good to see that the model is somewhat trying to achieve a goal based on what I would say expert would think makes sense. So because of the fact that we were able to create these two different models and come up with a list of features that were turning out to be important to making that prediction, we were able to explain or at least provide a rationale to these clinicians that the model is doing something that they would agree with. And then because of the fact that we were able to do these interpretations, we were able to go back to those neuroimaging data and then identify regions that turned out to be most important in terms of making those assessments. And as expected, at least in the context of dementia due to Alzheimer's, those regions that are classically known to be associated with disease, such as hippocampal atrophy, entorhinal cortex, amygdala, those regions in the temporal lobe, turned out to be the ones that were getting highlighted by the model as well. And on a few cases, about 100 or so, we collected postmortem data, right? On these people, they donated their brains, and their brains were autopsied and then histologically processed. And they were carefully graded by the pathologist, at least in terms of the degree of disease burden on those brains. And what you're seeing here are three different scores called as THAL phase for amyloid beta, which is a protein which is classically associated with the Alzheimer's disease. That's the first one. The second is this neurofibrillary tangles, which is called as based on a Braak staging, which is also very normally or routinely done within a pathology practice, especially in the context of Alzheimer's. And then finally, which is a neuritic plaque score, which is also another protein that is often observed to be highly present in people who have Alzheimer's, right? So these grades were done by the pathologist, and what we are showing here is that our model's predicted probability was proportional to the grade of disease, at least for A, B, C, and scores. A is the amyloid beta score, B is the Braak stage, and C is the CRAT stage. And statistically, we were able to observe associations between how the model's predicted probability increased with the degree of disease as well, right? That I think is a very great confirmation. In fact, if you talk to a neurologist or any clinician, they can tell you for a fact that Alzheimer's disease can only be finally confirmed in terms of diagnosis post-mortem. And these are the things that they observe post-mortem. And given the fact that our model was able to statistically correlate with the post-mortem evidence, I think that provided a huge important aspect related to validation that our model is doing something reasonable. And as an icing on the cake, what we did was we took the neuroimaging data and then we created those interpretations on those neuroimages. And then at the same time, we overlaid the degree of pathology burden colored here to show that those regions where the model predicted to have high degree of disease also all had evidence of high degree of postmortem pathology. Right? So that way we were able to visually show that the model is predicting in those spatial neighborhoods where there was observed pathology as well. And then finally, what we also, this is, I think, an important step, because ultimately, if you want to build diagnostic tools, we want to make sure these tools can hopefully be meeting that clinical standard. So here, one of the first things we did was we recruited about 17 neurologists, and we gave them basically the same data that the model saw, which means demographics, medical history, neuropsych, the same thing that they would normally see on 100 cases. And then we asked them the same question that the model was also asking, which is, can you identify based on this data whether the person has healthy cognition, MCI, or dementia? And if so, dementia, what do you think it is? Is it due to Alzheimer's or is it due to something else? That was a question we asked the neurologists, and 17 of them independently rated 100 cases each. But in the context of neuroradiologists, they don't really ask the same, we didn't ask the same question to them because they don't normally diagnose somebody with dementia. They basically look at images, they look at radiology images, right? So for them, what we did was we gave them only 50 cases who had confirmed dementia diagnosis. And then what we asked them is to see if they could point out whether that dementia occurred due to signs of atrophy observed in the context of Alzheimer's or some other etiology, right? So it's a different question for them. And here are some results where what we are showing is that the model seems to be doing pretty reasonable job in terms of comparing compared to the experts. The first row basically shows the dots there you're seeing are the individual performances of the neurologists. And then the plus sign shows the average performance of the neurologist, and the model basically is able to do reasonably well in the context of that first question. And on the second row, you're seeing is the performance of the radiologists who were able to discriminate between the AD causes of dementia and then non-AD. And again, the model seemed to be reasonably doing a good job in that context as well. I know it's already, 37. So I'm going to quickly, this is the first part of it. I know I took a bit of time, but I want to quickly go through that other part where we're also spending a lot of time, because digital data now is becoming like this new idea of how we can collect, hopefully, raw sensor level information, hopefully in a naturalistic setting, using how the person basically operates in their own daily environments to see if we can somehow assess the person's brain health, right? That's the trend of these days. And there are many ways to collect data, whether it's about gait, whether it's about speech, whether it's about sleep. There are so many ways of collecting information. And what we've been working on is, again, in the context of Framingham Heart Study, we started looking at speech as a modality of digital data to see if we can process speech using these automated approaches to assess if the person has, again, dementia or healthy cognition. Quickly, I want to talk about how the data was collected. So what happens is in Framingham Heart Study, participants come to the site, and then they go through this neuropsychological testing. So the examiner basically talks with that person and administers the neuropsych testing. That's usually about 2 hours long, 1 hour plus, but at least around 2 hours. And those sessions have been recorded. Those sessions have been recorded, and then we have access to all the data. And on those participants, we also have their cognitive assessments done. So we essentially have the data of 2 hour recordings of all these people and corresponding dementia status on these people. So we took that information itself, the data, the speech data itself, as the raw data, that allowed us to sort of process this information using some of these machine learning approaches. And in fact, Dr. Kiran and I have been working on this as well, where we feel like this digital data, hopefully collected in a more routine or more naturalistic setting, can allow us to hopefully inform about the person's brain health. Some of the background here is I just want to talk about why speech. I think it's a good question. I'm still figuring out why speech is the most important, but at least speech, I think, is easily collectible. Let's put it that way, right? So I'm not saying speech has everything we need, but at least speech is something that you can collect very easily. It can be collected in a home setting, in a more naturalistic setting, even in a clinical setting. So I think it has some value. It has some signal to think about, whether it's going to tell you whether the person has some speech abnormalities or whether the person has some cognitive dysfunction or cognitive abnormalities. That is something up to us to decide. It's too early to say. But given the fact that it can be easily collected, I think there is some value in terms of thinking about it, right? So, and we have been basically processing this data in the form of these approaches. One of the simple approaches to literally take the voice data, because voice data, if you really save it, it's like an MPG or WAV recording. It's like an hour long. So you can take the voice, and if you see the voice, it looks like this. And there are ways to sort of take the raw data itself without processing anything, and to see if you can build neural network approaches to take the raw voice and then use that information to build models to assess dementia. The other way people have done it in the past is to take that voice data and convert it or transcribe it to a text and use natural language processing to process that text to see if we can identify some patterns within the text. We have done both. We have published work on both. Right now we're trying to see if we can combine both these approaches to see if that can add additional value. And these are some preliminary results. In addition to what we do in terms of model development, we also are building these interpretable frameworks that can go back to these voice recordings in the same way like I showed before on the imaging data. We don't want to just neural networks to make predictions. We also want to go back to the data and see why those neural networks are actually making those predictions, right? And we can do the same things even on voice recording. So imagine you have a 1 hour voice recording, and if you process all of it, what if you actually go back into that voice recording and identify snippets in that voice recording to see which of those snippets actually are contributing to that output of interest, right? So those kind of techniques, I think, are going to allow us to understand and interpret the data that exists there. And we have done some of the work on that. But yeah, I mean, I think voice is very exciting. It's a very new data modality per se. Of course, there are many other digital data that is being collected. I think with Dr. Kiran, we've been thinking about collecting some gait motion data, some sleep data. We also have some grant that got funded recently where we're administering multiple different variables on these participants at Boston University Alzheimer's Disease Research Center, as well as at Framingham Heart Study. We so far have been going through this process of optimizing data collection. I don't think we have fully optimized it. There's a lot to do there. But I think there is a lot of potential for us to think about collecting this kind of data. I do not know where we'll end up with that, but I think there is still a lot of promise on that, right? So with that, I mean, I just want to conclude and then open it up for some questions. These are my kind of really high level summary. I think native data is something that we really like to use because like I showed in before on the MRI scans, it's the DICOM files. In the context of audio recordings, it's the WAV files. We feel like that has the most amount of information. And because I'm not a subject matter expert on neurology, I would like to rely more on the raw data itself rather than trying to derive features from these from the raw data. And we also are trying to build methods that can allow us to leverage that raw data and then use that raw data to sort of get better signatures of whatever question that we are interested in. And we also want to expand it to not just one modality of data, but hopefully many, many modalities that can be routinely collected. We focus extensively on data preparation, but I think even more importantly, we focus on model validation, because if you don't do that, it's very hard for anybody to get convinced. Even after doing all those things, I'm still not convinced on many things. So it's, I think, important to keep in mind that if you build models, we need to make sure these models are validated and they are generalizable across various different populations. I think that's one of the most important lessons I've learned. And ultimately, we are only going to be the developers. There are going to be some other people who might be the users, and they might be clinicians. So we got to bring them on board. We got to think about how to work with them. We got to figure out how to ask questions that they want to ask and sort of come up with solutions that hopefully can help them, right? So bringing them on board early on, working with them, I think has been a great learning experience for us. And we continue to work with them and we learn a lot of things from them. So that's the other thing that I've learned. And then, yeah, finally, I want to thank my sponsors and thank you for your time.
Thank you. We'll watch questions online. Charlotte will read them out as they come, and there's quite a few people there.
I
but-
see, how do I see the people who are on the, oh, stop stream, okay. Okay,
Questions, yeah, folks.
yes.
I'm really interested in the, well, first of all, fantastic presentation. I
Great.
absolutely love these models that focus on really clinically impactful work. I'm really interested in your focus on raw data specifically. So I know you work a lot with this raw data, but to what extent is it pre-processed before it's entered into these models? Because it seems like you're taking, say, voice data from a session in which someone is performing neuropsychological
Yeah.
testing, but you know, are you including the voice data of the clinician? Like what is
yeah.
actually being fed into the model?
Yeah, so right now we are feeding, so the goal is to not do any processing. Hopefully someday we'll reach there, but we're not there yet. But over time we've gotten better at reducing the amount of processing we need to do. For example, in the paper that I initially talked about that was published in Brain, we had to do a lot of work on image registration, skull stripping. Similarly, in the context of voice, we had to figure out how to convert all that into a spectrogram, for instance, or extract something called as MFCCs, which are one ways of extracting some features. But more recently, we eliminated the idea of registration. We eliminated the idea of even thinking about skull stripping, because ultimately, if a radiologist, I mean, what we wanted to achieve at the end of the day is, imagine a radiologist is looking at a scan for the first time. They don't register this. They don't do skull stripping. Just look at the image and then they figure out what's going on. So we want to get there. As thirds, we are reducing the amount of time on processing the data, because we don't want to do that, because it's just headache. Because problem is too much normalization or too much harmonization is also not good. One thing which I can tell you for sure is that, let's say you have data set coming from BU. Let's say there is a data set coming from, I don't know, MGH. Say you format this entire data set at BU in a nice Excel sheet, rows and columns, and to you, what are we doing? We want to fit, or we want to that stuff based on what you did at BU, right? So if you train a neural network, it's going to look great if you normalize and if you put everything in the same structure. The key is to actually build a neural network that is going to learn from your BU data set and then figure out how to do well on that MGH data set, which is unprocessed. If it can achieve that goal, then I think we are doing real AI. If everything is nice and cozy and nicely formatted, neural networks are going to do great. We don't need any. So that's why people are, of course, we've been spending a lot of time on that, but we want to minimize it as much as possible. I don't know if that helps, but
Yeah, absolutely.
that's the goal. Yes, sorry.
I guess sort of as a follow-up to Maggie's question, and again, this was fantastic. But how do you sort of determine that balance between the level of processing and
It's I don't think there is a definition to it. Unfortunately, I have had many times written papers and then got rejected just for that reason. And also proposals, even more so. I'm a proponent of reducing the processing, but I think there is the push in the community to force processing on us too, right? So we got to think about that. I don't have a good answer to it. I think it's something that I'm learning day by day. We literally got a rejection from a paper where we said exactly this, which we said we didn't do registration because we came up with a method where we don't need registration. And the comment was like, how the heck did you do registration? Because, this doesn't make any sense to me. We didn't do registration, right? So, but we showed the result. So there is that catching up that has to happen in the community as well. I don't know the answer, honestly.
Are you asking that because you're wondering how much cleaning of the data you need to do before you start putting them in the model?
Yeah, exactly, like sort of.
Start with fully clean and then go towards less clean as much as
And
possible.
then just validate.
Yeah, I mean, yeah, but how much are we going to do? I mean, think about these days. I mean, I'm sure you have seen the co-pilots and the chat GPTs around the world, right? So right now, you're not normalizing or harmonizing your data before you add a query, right? It's figuring it out. How is it doing it? Right? There must have been something going on behind, right? So as the generative AI is catching up, I think we need to think about reducing this. Hopefully, it's going to help us to reduce this normalization because that's the goal. We don't want you to spend hours and hours formatting a table. What is the point? Right? So hopefully, we'll get there.
So it's super exciting to think about the fact that we can kind of limit this pre-processed data as technology develops. But until then, I'm thinking of those initial models that you're presenting, and they showed that, which factors and variables were most helpful in predicting, MCI versus dementia or dementia due to Alzheimer's or another cause. Once you have those variables, are you able to strip some of those less helpful variables to limit the amount of process you have to do for that long list of assessments? And if you find out that something's not super helpful,
Yeah.
you
Yeah.
not have to use that move?
Yeah, we somewhat do that, but I guess the pre-processing that I think I was referring to is not necessarily to reduce the amount of data. I want to use as much data as possible. If it is not useful, then maybe the computer will figure it out that it's not useful, right? I don't have to remove it. I think that's the other part, right? So there is a lot of work on feature reduction, if you will, right? I mean, it's good, but why do I care if I have a computer that can process all this data, right? Maybe more is good. I don't know, right? So the simplification is a choice. I don't think it's needed. Personally, we don't do any of that because I think we can handle the data we have. But I think the data processing that I think we're talking about is not necessarily reducing the information. It's reducing the burden of processing, right? So there are two different things. Right. Sorry. Yeah. Yeah.
Yes, thank you again for a very interesting talk, and I am a professor from Korea.
Nice to meet you.
And visiting Swati's lab every summer and winter. So I found your talk on like a digital voice recording based dementia assessment very interesting, and I wonder whether it looks like it's more language independent because the it's the voice target features that you are learning for the computer. So I think, so my question is that, is it going to be more like a language independent measure of detecting dementia? If it's going to be the case, then if you have ever applied this method to other languages.
Great question. So I don't think it can be entirely language independent. I guess this is the reason why we're trying to come up with different approaches. One of the first things when you just get acoustic information, and then just use that acoustic information to see if there is something there, right? It may not be enough, but I think that was the first step to come up with acoustic level, or at least extract acoustic level information and process that using these neural networks. But on the other hand, we're also doing these transcriptions where we're converting all the text to, obviously, in this case, in English. But I think in the future, hopefully, if you have any voice recording, maybe there are ways to extract acoustic information separately and then maybe use these transcription services to extract information to some language and then use language level analysis. But I think there is a lot in voice. It's not just acoustic. I think hopefully more approaches can allow us to combine all this information. But as of today, I don't know if we have an acoustic level signal that is great, that's going to assess or help us assess dementia. But we are so early in this process, so I don't know exactly the answer.
Are you, sorry, about something behind you?
Yeah, my question was just, I know you said you're really early in it, but have you started to sort of see features that are important in terms of?
Acoustic?
Combine their questions,
Yes.
because I know why she's asking that
Okay.
question, because, and G can tell you some more that maybe there is something about pause duration and,
Yes.
and this delays and so forth that are common across language patients.
Yes.
So it doesn't matter.
You mean
whether you're-
acoustic or is it not non-acoustic?
Not so much fundamental frequency, but in the audio signal,
Yeah.
there are pauses and delays and hesitations that you mine as part of English patients who have dementia, but also, I don't know, Korean patients with dementia. I think that's sort of where you're going, right? I mean, isn't that that's an opportunity?
Yeah, I think so. I think, like, as you know, I'm not the subject matter expert at all on this. So, I mean, I'm just sending that signal into these, and we're building methods based on the raw signal, right? So perhaps, like what you said, the pause, duration, all those things are already captured. Maybe we're not coming up with a definition of that yet. Maybe we have to go back and see what actually that means, what kind of definition we can give to that feature that is actually getting extracted from the raw signal. So
That's to her point, that's language independent.
possibly, right? But again, like I said, we are simply dealing with the raw signal, expecting that it's going to give us as much information as possible. So that's why I think we need to work with the experts to get those specific features, right? Yeah, and I think language processing, natural language processing is a field that is exploding, as you know. So there are so many better ways now to transcribe a text from these audio recordings, even if the recordings have some noise, still you can do that, hopefully in multiple languages. So I think there is a language level assessment that also we can do in combination with the acoustic measurements and all the other things we can do. So there is a lot you can get from voice. But I don't know if voice alone is going to be enough, but I think it's a great way to start. I think there are a couple questions on chat.
I don't think, yeah.
Okay.
Okay.
I see two chat.
One was Charlotte herself, and then.
Okay.
Somebody who knows you, Aaron. Oh, yes, I think.
Sorry. Yeah, sure.
I was really interested in the performance in the classifier where you tried to generalize across the different data sets. And I did notice that, for certain data sets, you see that the MRI only model, for example, outperforms the non-MRI model. And then you see the reverse for other data sets.
Sometimes, yes.
And then you also see some different performance in general on the RLC values. Do you have a technique for understanding why the classifier generalizes better or worse across different data sets?
I think, first of all, let me take a step back. I think, what does it mean by performing well? Let's ask that question. Are we saying that, okay, let's say I have a model that says, okay, I have a 90% accuracy on BU data set. What does it mean good on the other one? Is it 90 or less? Is it 85? We don't know that, right? So, I mean, to be very honest with you, the academic work is being done is brutal in terms of defining what's performance metric is, what is AUC, what is accuracy, what is specificity. But at the end of the day, that's not what it matters. At the end of the day, what matters is whether it can be done in a specific real world setting. And whether it's MRI or non-MRI, why should it matter? Right? So I'm thinking from that perspective, but to your point, the data set the way some of these data sets have been collected, at least let's say in the Framingham Heart study versus a more clinical setting, they're completely different modalities, right? So MRIs have some less significance in community cohorts, whereas in the clinical cohorts, maybe there is a little bit more significance. So there might be a little bit of value. We haven't done that yet, but there may be a little bit of a weight differences between the importance of certain data sets in certain settings. But as I keep speaking with these clinicians, I realize that we as academicians, we think things slightly differently and they have different goals, right? uh, they don't care about specificity or sensitivity. They're like, okay, what? Yeah, are you going?
It's whether it's interpretable as or not. as
Exactly,
being
right?
sensitive.
And also, what am I doing? How are you helping me? That's the bottom line, right? Are you helping me, or is your model 90% accurate? Two different questions.
Excellent point.